So let's start. So a classifier kind of setting up what the problem statement is. You're given a training data set. We kind of already have seen this. You have a bunch of xi's, you have a bunch of yi's, and in the setup of a classification, usually yi belongs to a certain class. So it's not like a regression problem where you're kind of trying to predict a continuous value. I like to kind of draw examples so that you're able to connect with what is happening. So for example, this can be like an IMD classification or a Twitter sentiment analysis scenario where your xi's are going to be reviews or tweets, and your yi's are ones or zeros, which is basically indicating positives or negatives. And the capital N in this formula is basically the number of samples that you have. The idea, if you were able to bring this down into a 2D space, is something like this, where you have, let's say, green points, and you have, the green dots and the red dots. And you're trying to draw a line in a way where you can best classify, or rather best separate the two regions out. Best is something we'll talk about in terms of loss. Cool. Before we kind of get into the deep learning part of it, or the neural networks part of it, he talks about, in general, like traditional ML. Is there a question someone has? Cool. I'll continue. So the setup is of a softmax, which is very similar to a logistic regression. And you've kind of already seen this. We'll again see how softmax actually works. You basically take exp to something, exp of something which has two properties. Exp basically keeps you all positive, so that is good for probabilities. And dividing it by this numerator kind of brings everything down to the range of 0 to 1. We'll revisit this again. A very important thing about softmax is softmax, all it does is, given a set of numbers, you are converting those numbers to probabilities. So in our case, those numbers are basically activations, and you're trying to convert those activations to a set of probabilities. And softmax tendency is to push one number through. And softmax really works only when you have like exactly one class to predict. If you have more than one, it's going to pick one of them with the highest probability and push that out. If you have none of those classes in your data set, it's still going to push something out. So that is something to just keep in mind over there. And this softmax, or this linear regression, these are linear classifiers. And if you're talking in multidimensional space, it's kind of trying to draw a hyperplane, or like the figure that we just saw, it's kind of trying to segregate two regions by drawing a line. Kind of always something which really helps is looking at the sizes of the matrices or the vectors that you're working with. So in this case, if you look at this softmax, this multiplication, especially this W into X that we're trying to achieve. So W is a C cross D matrix, where each row basically is like IMDb review. Each row is basically a set of weights for each class. So maybe the first row could be something like, if it's a positive review, maybe these are the weights. The second one probably is like, if it's a negative review, these are the weights. And X here is going to be the review that you actually put in at a runtime. And this is going to spit out this vector, which will ideally have like, we'll post-process it in such a way that it ideally has, you pick out the max probability for a certain class. So that's how you kind of achieve this classification problem. Cool. Let's look at softmax. So I'm kind of drawing back.
Sorry, just a quick question. So
yep.
If you go back, just go back up a little bit. The X there, could you explain again what that bit is?
Absolutely, right. So so this is something. Should I mention that? So we assume you finished training. You finished all your training on your training set. You have this weight matrix, and now once you have this weight matrix, let us say you get in a new review, or if you're familiar on the image processing side, let's say you finish training on cats and dogs, and now you get a new picture of a cat, or a new picture basically, and you want to predict which class it falls into. So that is what this X is. Does that make sense?
Yeah, so that's okay. That's the your new input, whatever you're putting in, and that you're going to multiply by this W to get your prediction.
Yes, yes. And so that's how it kind of gets multiplied. So you get like the probability, or you basically get a number for each class. Which again, you can extend this back to the training set also, but in the training set, you're not going to just have one vector, right? You have a bunch of them lined up, and so then it becomes like a matrix into matrix multiplication rather than a matrix vector multiplication. Does that kind of make sense?
Yes, thank you.
Right, sure. Cool. So kind of revisiting softmax here. So this, yeah, drawing from Jeremy's slides here. Let's say you're trying to classify whether the image has a cat, dog, plane, fish, building. Again, to reiterate, ideally your images have only one of these, not none of these, and not more than one. And the last layer, basically, out of the last set of activations that you get is this output. Now, if you look at these numbers, you really can't do much. So what you want to do is convert them to probabilities. And the way to convert them to probabilities is basically what the softmax achieves. And the idea behind that is to use an exp. And exp has the property of keeping everything 0 and above. And the other property where if a number is slightly bigger than another number, the exp is much bigger than the other number. So you take the exp of these outputs and you get these values. Now we have achieved that it's in the range, it is greater than 0. Next thing you need to achieve is somehow to get a probability score, you need to bring it in the range of 0 to 1. So the simplest way of bringing it 0 to 1 is you take these numbers, sum them up, that's what gives you this 12.7, and you divide each class by that sum. And that's what gives you a probability. And you can kind of see in the denominator, that's what the sum of all the probabilities is, which adds up to 1. So yep, that's softmax. Does that make sense?
It does. But given that when you do an e to a number, it's always going to be bigger, why can't you just pick the biggest number from your output, because that's the one you're going to pick, because it'll be the biggest e to the x also.
That's a good point, actually, but I don't know what the specific reason for that difference is. I think it's just that you want to bring it back into a 0 to 1 so that you can look at it.
Because then afterwards you have this probability view of it, and then you have an idea of how good that prediction is. But I wonder why you'd want, I mean, yeah, outside of that, I can't think why you can't just stick with the highest number that you have in the output column.
Right. And actually, if you think about it, softmax also is has two parts to it. You have a soft and you have a max in it. So you're not explicitly picking the max out. You're doing a softmax, which is kind of, I think he talks about this in one of the previous lectures, where the soft part comes basically like, because we're doing all these kind of manipulations here. Because from what you're saying, you can actually look at the outputs directly and just pick the largest number, right?
Yeah, because when you do an e of a number, it's just going to be bigger. So
yeah. So yeah, that's a good point. Probably investigate some more and see why this is done. Could be for the, I don't know if it somehow helps us with the loss.
No, I think it's because if you do an e to the number and then you make everything within a probability range, then you know whether it's, is it a 20%, is it a 30%, and then you know how good a probability it is, regardless of the fact that it's the biggest number. So it might be the biggest, number, but a lousy prediction.
Yeah. Actually, there is some more discussion around that. Sorry, there's some more discussion around that where you actually, when you look at these probabilities, they don't talk about the true probability of finding something. It's kind of, this is kind of, I don't know, convolved. It took me a while to understand this, where this is not like there is 62% chance that you find a fish in this image. It's a little more nuanced than that. So I probably have another slide somewhere where I'll share that and we can talk about that. Cool. Next, going into cross-entropy loss. And yeah, cross-entropy loss is basically a great place when you have a great loss when you have a classification problem, because you're trying to achieve, if it's the right class and you have predicted it correctly with a high confidence, then you want your loss to be low. Whereas if it's predicted wrong and you're predicting it with a high confidence, then you want your loss to be high. And to kind of put that, I have, where is that? Yeah, here. So let's say you're predicting a cat or a dog in this image, right? And this image actually has a cat, and you spit back a probability of 0.9. So that means your model is doing a good job. There is a cat, you're predicting with a high confidence that it is a cat. So your loss, you see, is a very low loss. Whereas on the other hand, if you look at row 3, it is a cat, but the probability with your, I'm going with a half-ish probability for both cat and dog. So basically this is an not a confidence situation. And you can see that the loss is 0.3, so it's much higher than this. I think when I was cropping this image, I missed out the last one. But yeah, it's pretty simple to run this. And if you have a worse confidence for a cat, you see kind of the loss shoots up even more. And at the end of the day, that's what you're trying to achieve with this loss function. So to kind of quickly go through this, oh yeah. So a couple of things to cover here is softmax. What is log softmax? You have this stability trick, you have negative log likelihood, and you have cross entropy. Why are we taking the log over here? I mean, to achieve the log softmax, it's kind of a neat trick where you don't have, because log of A by B is log A minus log B. And that's kind of what you achieve with log softmax. That's basically just applying the log to the softmax function. And what is cross entropy? Like we already looked over here, it's the same thing, but written mathematically, it's the negative of the log of whatever your predictions are. There is a term over here which you will usually see before the log pi, and that is basically which class does it belong to. And why does that simplify to this is, if let's look back at this again, which really makes it easy. The log of pi is basically this part, right? You take the log of the probability. And so if that's a summation, you'll end up with, yeah, okay, here's where the formula is. So this QC is basically the probability 0.9 for your first class that you want to pick. So that is cat. So that becomes 1 into the log of this. And in the second scenario, it will become 0 into the log of this. And that doesn't hold because it's 0. And you can see that this kind of always holds. You're going to only be picking out one class because the other one's always going to be 0. And this extends to multiclass too. An important thing to remember is not to confuse where to put in the predicted value and where to put in the actual value. Kind of something that I remember, the way I remember it is log of 0 is something you don't want to do. It's not defined. So and your classes are always in terms of 1 and 0. So you never put in that value here. Your actual values always go in a much more stable situation to put a 0 in over here.
So I guess this kind of also explains the previous question, why you do softmax.
Yeah, that's what, like I was kind of getting to the loss, right? It explains the loss and to kind of work with that. Cool, so that was the log. So let's kind of cover, yeah, so cross entropy is nothing but negative log likelihood of the softmax. And if you put all these together, that's what like the function is cross entropy. Hang on, let me just check the chat. Yeah, can everyone please mute unless you have a question? Please go ahead and. Cool. All right. So this negative thing is kind of an interesting thing. I was kind of looking at it, and I realized that the probabilities are always going to be in the range of 0 to 1. So if you take the log of any number between 0 to 1, that kind of gives you a negative number. So that's why you add this negative in there, so it kind of cancels this out. It's just kind of interesting. Cool. The stability trick right now is you don't want to deal with exponent values, exponents of large values. That kind of leads to overflow problems, and you want to avoid that. So a neat trick for that is someone is there who is not muted. Can you please mute? How do
Can you mute everyone? I think you can do it.
Mehul side. No, we just have the mute.
Does anyone know how I can mute? I guess it's fine now. Let's continue. Cool. So with the stability trick, okay, hang on. All right. Okay. So the next is the stability trick. So yeah. So you don't want to lead with exponents of large values. Simple trick. You multiply the numerator denominator by c. That is some constant, and you can pull this back in because e to the power of log c is basically c. Is c times log of the exponent, and the log and the cancel out, so it's c times that. So this is how you kind of pull that in. And now the thing is, what you usually set this log c is to max of a. So if you think about this, if you have a set of numbers, actually I pulled this down, I was trying something today. Oh, right, okay, yeah. So yeah, this is the same thing, right? This, you're just adding in e power a, e power minus a, so those cancel out each other. But then this is log of a product. You can write that as log of e power a plus log of the other term, and you end up with something like this. And you're doing xj minus a, where a we said we would pick as the maximum of whatever the numbers are. So let's say you have these set of numbers that you're trying to convert to a probability. So you find out the max of a, and I calculated these two. So P basically is if you were to do it the usual non-trick applied way, whereas N is the one where you're applying the trick to it. And I can just do the X and keep appending it. So if you look at this on the left-hand side, the first column, if you kind of look at it, are the A values. These values, the second column is without the trick, and the last column is with the trick. So you can see for the last one, when it's 100, you already got like 2.6 e power 43. Whereas here, you kind of e power minus 44, but remember that this is in the denominator, so 1 divided by a large number is basically going to be close to 0. So when you're doing this x minus a part of it, what happens is you're truncating everything to a maximum limit of x minus a, so max minus the max will be 0. E power 0 is 1, so you're truncating it at that limit, and everything is kind of going to be smaller than that. Just trying to plot that out over here, and you can kind of see blue is the one which kind of really shoots up, whereas, yeah, I mean, this scale is really bad. Everything is like 0 or lower there. So that's kind of just a small experiment to kind of look at it visually, if that makes sense.
Yep. Sorry, Prashant. Hi, this is Sagar. So I wanted to ask you something. What's the implementation, I mean, practical implication of the stability trick? Because I have gone through the lecture. I couldn't find anything relevant to that. So can you kindly explain why?
Right, yeah. So that's kind of, the stability thing is an issue because imagine if you have these really huge numbers over there and you keep adding, you're going to end up with an overflow problem, right? Because your computers are discrete units, so they can store like a certain maximum value. You cannot keep adding on to that and expect it. It will finally become an infinite number or a NAND. That is the reason why you don't want to end up with X of large numbers. So this trick
I got
keeps everything contained.
Perfect.
Does that make sense?
Okay. Yeah.
Cool.
Yeah. Perfect. Yeah. Thank you so much.
Yeah, I explained kind of something how I remember what P of C and Q of C is. Yeah, I think that's a good point for me to ask. Do you guys have any questions up till here, or shall we proceed?
So I have, I wanted to answer the question, if I may, regarding the exponential. That's my perspective. I may be wrong. So I had earlier doubts. So what I read was initially when SVM, like normal kernels, were used, at that time, the exponential function, what it does is it basically bifurcates the larger numbers with the smaller numbers, right? So if you do exponentiation of a larger number, that would be much bigger than the exponentiation of a smaller number. So that would be much smaller. So to get the linear decision boundary between the larger number and the smaller number, exponentiation was used. So basically this the exponentiation that's been used in softmax or logistic regression, I think that's the basic motivation behind it, to get those numbers as far apart as possible. Does it make sense? I mean, that's what I could understand.
I think, yes, there is some truth to that, but I don't think that kind of helps you in a linear way, because X is basically a curve, right? So let's go back here. So yeah, if you look at this, e power X is going to do this.
Yeah. So if you see that bigger numbers, suppose we are comparing X equal to 2 and X equal to, say, -3, right? So in that case, for X equal to 2, if you see that the curve goes to infinity.
I see what you're saying.
If you compare,
right.
Yeah.
So right. So you're separating in terms of you're trying to widen the gap between the two as much as possible.
Exactly. Right.
Right.
Yeah. Yep. So that you can draw a decision boundary.
Right. Okay. Yep. Cool. So anything else? Does anyone want to add something else that I've missed or misspoken in between, or shall we proceed? Cool. I take that as let's proceed. Yeah, but just wanted to kind of, I don't know if this is covered here, but I thought we should kind of look at what underfitting, overfitting is and how it's kind of related with bias and variance. Given a set of data that you want to work with, and let's say you have like 1,000 sample points, you kind of split them up into your training set, validation set, and your test set, just following like a 60, 30, 10 percentage to split this up. And what exactly is overfitting now? Overfitting is, given these set of points, your data, your model is kind of going to replicate this and follow this trend really well. But this is something you really don't want. Another way to think about this is, if you overfit your model and you run your accuracy or whatever metric you're trying to run on the training set, you will get really good numbers, really high numbers. But the moment you remove this and you remove your training set and you apply it to your test set or your validation set, your accuracy or whatever metric you're looking at is going to drop. That is a kind of a sign for overfitting. On the other hand, yeah, so this is otherwise referred to as like a high variance problem. On the other hand, this is underfitting. This is if you have the structure of data and you say, okay, fine, I'm going to fit a linear model to this. And now this scenario, what is happening is your training set error is going to be bad. And your test set error is also going to be bad. Your metrics are going to look really bad on both the scenarios. In the high variance or the overfitting scenario, the other way of thinking about it is like your model is kind of memorizing all the data and being able to identify that. It's not able to generalize that well when it looks at new data. So an ideal situation, what you want is kind of a low bias, low variance situation, which is fitting it something like this. And this kind of, again, covers it the same way. Cool. So now let's kind of jump into the neural network approach, where till now we were discussing was kind of...
Sorry, I have a question.
Yep.
overfitting aspect. So you're doing a model that is, let's say, for instance, predicting a rate pricing just for conversation's sake, and you want to be like you want the delta between the predicted value and what would be the market rate be less than, let's say, 1% or 5%. Would you say overfitting would be like the ideal way to, if your model was overfitted, would be the ideal way to like handle it? Or, and to what extent does one decide that this is now, the overfitting in this case is too much and I'm going to reduce, I'm going to do this and this? Like, is there some conventional rule or some...
Right. Yeah, that's a very good question. And I don't think there's a conventional rule. It's kind of on a case-by-case bias. Case-by-case basis. And I don't remember where, but somewhere it's like, if you were, for example, trying to win a competition on Kaggle, literally till the third decimal place, your accuracy matters, right? So in that scenario, yes, you don't want to be overfitting at all. You want to build as generalized a model as possible, but at the same time, get a good prediction. So it's kind of a trade-off there. So that's what the low bias, low variance trade-off is. But on the other hand, like what you were talking about, something like marketing, it's the question is like, how much of an error are you willing to take in your predictions? That's kind of the best answer that I can think of. Is there anyone else who wants to kind of chime in on that?
Yeah, the one thing Andrew NG has mentioned in his deep learning.ai class, he says, like, you mentioned the training set and validation set, right? So let's say your training error is 5%, right? And then your validation error is around 10%. So that's a clear sign you're overfitting. So he normally, his rule of thumb was, look at your training error, look at your validation error, and say they're around the same. Say they're both 5%, or say training is 5% and validation is 6 or 7. It's okay, and that's how he's like talk about overfitting and bias.
True. Okay, that makes sense. Like for the other, just kind of the other side of the coin on that is you don't want to be having an underfitting situation, right? Like in the cases of errors, you don't want your validation error to be much higher or lower. Hang on.
Lower. Yeah, you don't. Yeah, you don't
lower.
want your training error to be 10% and your validation error to be 5%.
Yep.
So there's also the other discussion we had on fast AI. So when you're initially training, you want to be overfitting a little bit.
Overfitting, right.
Overfitting is like basically when you see your validation loss getting worse. So initially you want to be overfitting on your training data, and then your validation data. If the loss keeps going down, you're not overfitting. But if the loss on the validation starts going up, then that's when you start overfitting.
Right. Cool. Yeah. So just continuing with that. So you kind of always have the first attempt should be to overfit your data, and then you kind of apply the other regularization and other techniques onto that to kind of bring it back. So anything else?
Nope. Thanks, guys.
Just a general question. What this word variance related with overfitting? What it exactly? I understand what overfitting means, but it's high variance. What does this word is telling you? What is like high above the variance?
If you look at something like it's kind of like a variance between these 2 points that you're trying to predict. So let's say if you were to draw this line. If you're able to see my mouse, this red line, which is a smooth kind of curve, and then if in the overfitting scenario, you're predicting these values.
Okay.
Right. So if you look at it, the variance the variance across like this, that is going to be higher. Does that make sense? That's where the high variance.
Makes sense. And similar to the underfitting, can you explain high bias little bit underfitting?
high bias in that sense would be, if you were to look at the bias, does anyone else want to chime in? While
yeah, hi Prashant.
Yep.
I would like to join in. I'm sorry for interrupting. So, referring to the question, basically bias and variance, the term, they come from the mean square error. So, if you see the points for the underfitting, right, that there is a single line, and if you try analyzing the Euclidean distance between a point, drawing the straight line between the point and line, predicted line. So, after summing it over, the entire value should be low. So that's what the bias is. I mean, the bias refers to the summation over xi minus x bar whole square. That's the statistical representation of bias.
No, but okay, just I'm like the loss. I know the loss. The MSC, you are trying to minimize it, but the word bias is how it's connected. What does it trying to tell you that it's a highly biased?
Okay. So what high bias is when your model is too simple for the actual data.
I think you have to.
And in this case, the model in this underfitting, the middle plot there, your model is linear, but the data looks like it's quadratic, right? And so what you're seeing is a high bias because the best model you have is linear, but the data itself is quadratic, and there's nothing you can do about it. There's just going to be a very high bias. That mean squared error is going to be very high. So that's what the high bias is. The reason why the high variance is what happens if you've overfitted your model. That means you've fitted your data to a model that has a lot of flexibility, and as a result, you fitted the data to the noise. You fitted your model partially to the noise, and that means that if you throw some more data at this model, it's going to be way off because the noise in the new data set's going to be different. And so you're going to get a lot of variation, and that's the high variance when you've overfitted. Does that make sense?
Yeah, it makes sense. Just to chip in, like what I'm thinking in terms of just the word, not in a machine learning term. So it's like a high bias. For me, what I'm reading is that model is kind of like a stubborn. It thinks it's linear. And that's what I'm going to give you. And that's my opinion. And it's very opinionated model here. That's the bias. It doesn't matter.
Yeah, the bias is the difference between your model and the actual data. So if you have data that follows a quadratic distribution and you're fitting it with a linear model, there's nothing you can do about the noise, about that mean squared error. You're going to have a huge difference between the points in your model and the points in the data. That's the high bias.
Yeah.
If you on the other hand, if you were to choose a quadratic model, you would fit the data like in the third frame there, and then the mean squared error would be small.
Yeah, makes sense. Thanks, guys.
Oh. All right. Okay, so till now we kind of dealt with linear models where we were kind of working in, we drew this kind of boundary line, but we were really not able to grab these other green points which are out here. And you wanted kind of a nonlinear decision boundary for this, and that's where neural networks kind of step in. There are other approaches. I think if you go in like higher degree polynomials and those kind of things, you should be able to get nonlinear decision boundaries. But yeah, we'll be jumping straight into kind of these, the neural networks. Okay, the other thing which kind of is interesting over here is if you looked at the image processing, kind of the deep learning networks over there, the models and the architectures, how we build stuff over there, we were always training the weights. Here, the interesting thing to note is that you're actually training the representations of the words also. So each word over here is kind of also, the representation of that is also kind of getting updated. So that is able to move around in your space, and you're able to kind of help with creating these nonlinear decision boundaries. Yeah.
Real real quick question. What is that upside down delta thing? How do you say that?
Okay. So the upside down delta is basically called nabla, which otherwise is the gradient, which is basically kind of like what you're calling a differential. So this, let's look at this kind of J is your loss or your minimization. I mean, the function you're trying to minimize, the loss, the error, multiple terms for that. Theta are the parameters that kind of represent. So each word is basically a vector of numbers, right? And that is the theta. Sorry, these weights all together put the theta. So J is a function of theta, that is loss is a function of theta. However you change this, the loss is going to change. And now you're trying to differentiate the loss with respect to this theta. In other words, that future we'll see what is backpropagation is trying to differentiate your loss or find the gradient of the loss with respect to your input parameters. And careful with that, it's not the input, but it's the input parameters that you're trying to change. The input is something which is given to you, you cannot change that. So in other words, that's a gradient. I have a slide which kind of covers that too. So let's continue. When we come back there, you can, if that doesn't make sense, we can continue. Just to kind of relook, yeah, sure. Look at the size of this matrix, CD plus VD, which is basically, you have, V is basically all your vocabulary terms, right? The number of words that you have. And then C over here, if I'm not wrong, is that the number of classes that you're trying to, I think, segregate them into? Yeah, I think that's what that is. And D is basically the dimension of each of these like word vectors. And since you're concatenating them, they need to kind of align up like that.
Sorry, Prashant. Hi. So in this particular slide, I had two questions. So in the lecture, the professor had mentioned something about, if I got it correctly, it was interaction terms. So I was wondering, I mean, why would I like to add interaction terms to my model, and how would intermediate layers learn to form the interaction terms? He mentioned something about this. I'm not too confident about this. Can you please explain on that?
That kind of jumps into the deep learning side of it. So let's kind of build up to that. So let's say if you have, like someone suggested an example where you're kind of trying to predict the price of a property. And let's say you have two features, the number of rooms and how far the house is, let's say, from the city. And now you build like a simple linear regression model and you are able to predict the price. Now, what the interaction term kind of means is that you want to take the fact that the house has 3 bedrooms and it is far away from the city or near to the city, kind of have an interaction between those two. So a simple way to do that is multiplying those two vectors and adding that as a new feature. So now instead of having two features, you would have 2 original features and this third feature, which is that interaction term. So that's kind of how you would manually go about doing it. Now, when it comes to the deep learning or the neural network approach, you manually do not do this feature thing, though you could, but you don't have to some extent, because the network is going to kind of find out what these interaction terms could be, and it's going to encode that kind of in your model weights. And now the other question could be that, can we look at the features and identify what this interaction is, which is kind of hard because it really doesn't have to be 2 interactions that are just getting combined together. And even if it's just 2 interactions getting combined together, you don't know if it's taking the square of one, the cube of the other, or in some matter like that. But does that intuition kind of make sense?
Yeah, I understand that. Okay, I mean, so going to that, I mean, if you're trying to understand the interactions, I think that would go into more XAI, like explainable AI, trying to understand how the layers work and getting a perspective of that. So yeah, that's going into argumentation theory and defeasible reasoning to an extent. But then anyways, regarding the interaction terms, so you mentioned like if there are 2 features, say A and B, and we want to combine them, use a dot product of them, and use it as another, basically feature engineering, and use it to train the model. So don't you think that, I mean, providing extra features, I mean, instead of using A and B, we can combine them A dot B and just use A dot B, right? Instead of using all the three features. So that's what my perception is, to basically eliminate all the redundant features and use the ones that are relevant for the model to train. So I mean,
so if you want to get into redundant features, then how do you know that A and B are redundant to start with? This is kind of like an iterative step. If you want to do that approach, you kind of use A, B, A square B, B square A, and A square B square, etc., etc. You train your model. Then you can kind of start looking into your model, probably pull up a feature importance plot. Now you see what are the features that are not that important. Try removing those out, retrain your model, and see if your accuracy is somewhere around in the same region.
Okay. Does that make sense? Yeah. Okay, cool. Yeah, perfect. Yeah, thank you so much. Yeah.
Cool. Yep. All right. Yeah, this was something that was mentioned in the slide that I was not able to pick up. Does someone else want to mention that? I kind of forgot where it even came. Oh, I don't remember where that is. But yeah, there was a mention of that where, if someone remembers, this was kind of the lexicon term where you had all the words, and this was kind of the, I think, the embeddings that he was using. I really didn't understand this part. Does someone else remember what this was or want to add something to that, or else let's continue? Cool, okay. The other thing that we talk about is you have this huge matrix because you're having like all these vocabulary words, and each of these words are kind of represented by a d-dimensional vector. And now if you want to go into that matrix and look for a certain word, where the word, if it were to be one hot encoded, you would have like a ton of zeros, and you would have like a 1 at a particular place indicating that word. So let's say it's the 17th position, so you have the 1 over there, and you want to pick up the 17th row, you can actually take that matrix and multiply it into this vector. But that is mathematically and theoretically the same thing. It will work, but it's super inefficient. So something that is kind of always mentioned with embedding layers and stuff like that is, given that you can just directly pick out the 17th row or the 17th column, depending on your situation, and that is kind of makes things easier. Cool. So let's jump into, a single neuron where you can use that to do a binary logistic regression, trying to do something like true or false, positive or negative. New terms coming in here are, you have F, which is a nonlinear activation. This is something that introduces a nonlinearity in your model, which is a super important thing. We'll look at that. W are the weights, B is the bias. Both these put together are called as parameters. H is the number of hidden layers that you have, or the hidden units or neurons, and X is your input. So now let's say you're given this X input. What you're trying to do is you're multiplying this X into this weight matrix W, adding on this bias, and then applying this activation function to it. What is this activation function going to be doing now? This activation function basically is incorporating kind of this nonlinearity term. And we have a bunch of slides that will look at this towards the end. Just kind of take this at face value right now. We can get back to this if you have some more questions. An important thing to notice is, like in ANNs, you have this term where the bias is kind of represented with a +1. So what this means is, if you were to look at this equation, so you're doing W2 into X, where X is this vector which comprises of X1, X2, X3, and 1 right at the end, and you're multiplying this W into this. So if you go back to this original slide, this one, so you're doing this, which is you're grabbing this row of W, and grabbing this column of X, which was basically X1, X2, X3, and 1, and you're doing like a dot product between these two, right? Now, what happens when you have a 1 at the bottom? The one at the bottom basically is you're kind of triggering this activation to be like a bias term. And what exactly is that bias term is, do I have that written somewhere? Yeah, okay. So if you were to look at just one neuron, you have your input, you pass this W1, it comes out through the activation. Since there is no, that you can see there is no that +1 or that bias is not being added, you kind of just get back y is equal to mx. And this model pretty much can just tell you this. There is no intercept term if you're looking at in terms of y is equal to mx plus b, that plus b is really not here. So how do you kind of want, if you want to represent this model, which kind of moves this line further above, further below, and you want to simulate that. So what you do is that's when you add this bias term in. And now if you look at it, you get W0 into X plus W1 into this, which is always a 1. So this W1 right now is what is your bias. So this bias kind of helps you look for like I kind of think of it like as pre-existing notions that you already have. If you remember something with respect to embedding layers, it's kind of, this helps you encode. Let us say I am someone who likes to review a lot of movies and I review everything. I'm a positive person and I have a tendency to review everything, let's say 0.5 higher than someone else who is rating. And that person's bias probably is that they kind of are very negative to some extent. So they always rate everything -1 more than what the general average people would. So that's kind of an intuitive understanding of what bias is. So that's kind of talking for this bias term. Yeah, and then when we move into the neural network thing, we don't kind of use, at least I haven't seen us using this bias is equal to 1. Like externally, you basically set up like a vector and you initialize them to be the ones, and there you have the biases that are kind of getting updated when you run your SGD. Here, though this is the bias which is 1, it's W1 that is kind of the actual bias, and that is what is kind of getting updated. Does that kind of make sense?
So it's just
well,
kind of.
I'm kind of.
Yeah, go ahead.
Yeah, sorry. Go ahead.
No, go ahead.
Okay, so I'm kind of confused, I mean, regarding the bias term. So I had referred to Andrew Ng's course. So he had also mentioned something about the bias, but I was not confident enough because bias normally I've seen used in perceptrons in the same way that you have described right now, with bias equal to 1. That's how I mean, you don't started.
Right.
But why are we trying to do this? I mean,
so that's what I was saying.
Why are we trying to do bias? Yeah, please.
Yeah, so just the way I kind of understand this is like, let us say if you were looking at movie reviews, like let's go to like kind of the IMDb review stuff. And on average, you kind of know how people are rating certain movies or their tendency. Now if you talk about movies and users, actually, let me make that clear that there are 2 bias terms. There is one bias term for movies, and there is one bias term for the user. So now let's talk about the bias term for the user. So the bias term for the user is going to be, how do you, Sagar, in general tend to rate things? So this is like a constant that is always added. So let's say your model kind of predicts, okay, Sagar is going to rate this with a certain probability, with the certain number of stars. So you get that output back. But then you need to add this term onto it, which is the bias, which basically says, oh, okay, Sagar is in general a positive person. So he rates things, let's say, with the 0.5 more, the number of stars. So that's what kind of the bias is doing over here. Does someone else have a better explanation to that?
Well, I have one that I got from this book, you know, the Online Neural Networks and Deep Learning book, which is interesting. And what he said was, he gives this example of a cheese festival. There's a cheese festival in town, and there's 3 factors that are going to determine whether or not you're going to actually go. One is how difficult it is to get there. The second is the weather, and the third is how much you like cheese. He said, if you really love cheese, that, you know, you give it, say, a bias of 6, and the threshold that you establish for going or not going is 5, it doesn't matter what the weather is, and it doesn't matter how difficult it is to get there. So he also said that it's essentially the threshold that's then flipped to the other side of the equation, which I don't entirely understand, but I kind of do. So that was that was kind of illuminating in terms of a bias can instantly push you over the threshold or make it very difficult to get to that threshold if it's very low.
Mm-hmm.
So sorry, David, are you saying that the bias acts as a threshold value for for predict something upon?
I mean, I think so. I don't entirely understand this, but I think it's certainly, just in the sense I just described, it will make it, you know, it will make the activation function, you know, pass the threshold or not pass the threshold, depending on how it's adjusted. That's my understanding anyway.
Another intuition is like if you look at just a simple linear regression, which you have there, y equals mx plus b. So if you don't have bias, you're forcing the line to go through origin.
Right.
Yeah. So.
Yes, that makes sense, and that kind of fits with what I was saying in terms of it's this number that moves things up or down, you know, the intercept essentially.
Yeah, so I mean, the other way, if you want, just to put this, like, if it were to make sense, let us say y is temperature and x is like the number of bacteria that you find in a place. And so m, let us say, is 2. So based on how the input, the other way around, x is the temperature and y is the bacteria that you find. So as let's say m is 2, so as x increases, y, the number of bacteria, is just going to double, right? But what if the situation is that you already have like 1 million bacteria already present, like at base level? So that's when you kind of add that b, which is again just another representation, I think. Does that help?
Okay. Yeah. I mean, the bias term can be greater than 1, right? We are choosing 1 because we are assuming from the perspective of like having probability to be maximum 1.
That's a good point. That's what I was trying to explain over here, where bias is actually equal to 1, which becomes W1 into 1. So W1 is actually what is representing your bias over here. So if you look at this, if you look at this function over here, it's sigmoid of W0 into X plus W1 into 1, which becomes, right? And this is basically y is equal to mx plus b, where this b is nothing but W1. And yes, it can be any value. So the 1 actually is nothing to do with bias. It's just to set a bias which is W1. And W1 is the actual bias.
Yeah, and I like your explanation of bias from the point of view that it gives the model the flexibility to take into account that each user, if you're rating movies, for example, could have a bias, and it makes your model more flexible to take that into account. If you don't have a bias term, then you're basically assuming as a prior that everyone has the same rating system. But when you add the bias, you're giving your model the flexibility to reflect individual preferences as you know, and it makes the model more accurate.
Yeah, you can apply that same bias now. If you think about it in terms of movies, there are just certain movies that people like. So you want to accommodate that also within the movie rating, so that you know that, okay, this movie is liked by a lot of people, so the bias is going to be like everyone's just going to rate it plus 0.1, maybe because the actor in it is loved by everyone. So it kind of helps in that part.
Yeah. So can someone describe a little bit about how, so what does this apply to? By which I mean, I have a bias, I like science fiction movies. You have a bias, you like romances. Does this mean what does this mean in the larger picture? That if we just say, the bias for science fiction is 0.5 and for romance is 0.3, what I'm trying to figure out is, does this mean that the neural network includes a kind of a range of biases that it may then use in its calculations?
Right.
Or is it that, an individual just has these biases? That's does that make sense what I'm asking?
Yep. So yeah, going back to that. So each user has a bias and each movie will have a bias. And now bias is something that you are not going to set, but it's going to be like a learnable parameter that's kind of going to get updated by the neural network. And that is going to set this bias, which is going to kind of take care of, you liking romances, you liking, let's say, movies which are action-driven or horror movies. It's going to kind of encode that within that bias, and it's going to hold it.
So if the model is sorry, if the model is shown, say if you are known to like action movies, if it's already solved that parameter and found that you have a bias towards action movies, then what happens is that if it says, what is this guy going to think of this new action movie that isn't even in our model, it's going to automatically increase the rating by your bias. Because it's going to predict that, if it's an action movie, this guy's going to like it more than average. So we already know something about the way he's going to rate it.
Right. Go ahead.
Okay, that makes sense. So it's being learned. It's then applied to this user, but it's also probably applicable to other similar users.
Not applicable. I mean, each user would have their own bias. So there is a bias tied with you. There's a bias term which is tied with me.
Yeah, but still, I imagine there's a generalization feature here as well, or whatever the term is, not feature that's used. But there's a generalization possibility as well, because if we know that I have a certain profile with biases and there's a new user that kind of likes the same stuff, that would help predict for him or her as well. That's all, I guess, what I'm saying.
Okay. Kind of the other way. Like, I think the thing to kind of remember is that there are two biases here. There is one which is associated with the movie, and there is one which is associated with the user. So kind of both of them play together and interact with each other. And like you said, the new user thing, that kind of gets into a little more discussion, I guess.
Okay, thank you.
Hi, I just wanted to join in. So, I mean, the bias term would not be different for each user, right? So if you have one model, there's going to be a fixed bias value. Like once you have trained, you get a bias value, and that's your bias value. The bias value is not going to change for each user or each row, each observation. Once you train your model and you get a bias, that's the bias. I don't think it changes for each example. I mean, once you give it an example, it's not going to have its own bias, right? There's just one bias. Once you train the model, you've got the value. It does not change again, right?
The way I am looking at it is, like, for example, if you
unless you have a different model for each user, there's just going to be one bias value. I mean, that's how neural networks work, right? Once you have trained the parameters, you've got the parameters fixed. There's not going to be a different bias for each user. That's what I mean, that's how neural networks work, I think. Yeah.
I kind of understand what you're trying to say, but the explanation that I was trying to give is like in terms of like a recommendation engine or something that you're trying to build, where each embedding vector is associated with each user, and in that scenario, each row is going to have an individual bias. There, the bias is not going to be the same for all the users, and applicable similarly to each movie will have an embedding vector and a bias associated with that movie. Again, the biases across the movies is not going to be the same.
Okay, I'm not sure of that architecture. Like,
that's what I mean. That's why I think you bring up a good point. With respect to this, the bias here, W1 is going to remain the same, but that's what I don't think I did a good job by bringing in the user movie thing.
I was a bit confused when you brought in recommender systems here.
I was just, intuitively, that kind of makes sense there. But I think if you're trying to look at it as this single perceptron or and ANN. I think David's explanation with the cheese thing is kind of the best explanation.
Yeah. Or you can just think of it as it's just a function approximator. So just to complete that function, you need a constant at the end, right? You are just multiplying weights with all the features, and then you need a constant. That's how logistic regression works. That's how linear regression works. Just to complete that equation, you need a constant at the end. And that's what a neural network basically is. It's just a function approximator. You give it some features, it gives you an output. It makes its own complex function inside, and it gives you an output. I mean, that's all. I don't think there's a need to complicate it. You're just adding a constant to your equation. That's all. Yeah.
Yep. Cool. Yeah, it's already 11:10, and we have a bunch to cover. Do you guys want to do it next week? Do you guys want to continue? What is the general consensus?
I could keep going for a little while.
Or should we just continue, and maybe since it's getting recorded, others, you want to just catch up later? Is that fine, or?
Yes, that's fine.
That sounds good to me.
Okay.
So I think some folks can stay on, but I've got to run. I definitely want to go through the rest of your slides. I think we're about halfway through your slides. So if you don't mind, if you don't mind continuing the other half next week, that would be great. But I know there's some folks who want to just keep talking now, so I don't mind.
Is it fine since it's recorded, do you think you'll be able to kind of catch up somewhere in the week, or is that going to be hard for you? Or do you want to do it and ask questions next week?
Yeah, I can do that so you guys can continue. If wherever the group stops today, though, if we could pick up there next week, that'd be great.
Yeah, and we keep some time in the beginning to clear if anyone has questions regarding this, and then we can proceed.
Okay, thank you so much. And thank you for putting these slides together. They're really great.
Absolutely, no problem. Cool. So let's kind of proceed. So traditional statistics, this is what you kind of have. You have your inputs. You kind of have these predefined rules. So given a data set, you make an assumption. You look at the data and you say that, oh, okay, fine. This data looks like a linear model will work. And then you put in those rules. That's what your rules are. And you spit out your outputs, calculate MSE, and proceed like that. The main difference with machine learning is you kind of have these inputs and you have these outputs with a good amount of data. And you're telling your model, you go and figure out what the rules are. And now once you have what these rules are, then if you're going to make a prediction in the future, you use your new input that comes in, you already know what the rules are, and that's what kind of spits the output. So that's, what is this? Okay, so this is kind of the end where he added in one more layer. And the important thing which I kind of took away from this slide was these hidden layers is giving the ability for this network to kind of build these nonlinear representations that it wants to. And at the end of the day, though, this is kind of like a logistic regression itself. It's going to predict whether it's going to be a positive or a negative output. So let's run through this from left to right. You have a bunch of inputs. You pass them through these neurons. You get a certain output, which is again passed into this other layer. And this layer now is followed by a nonlinear function, which is very important. And that nonlinear function kind of spits out a certain prediction for this specific input. Now you look at what the expected value for this input was, whether it's a positive review, whether it's a negative review, and you see how bad your model is at predicting it. And you kind of use that information, go back, update these layers, weights and parameters, and you kind of proceed. Go through this again, just kind of a quick dive into that. Yeah, so this is what he was kind of talking about, like how things have moved from neurons to shallow networks to now, which you kind of deal with deep networks. Looking at the above model, how it works is writing them down as a function, right? So I've kind of drawn this figure out where you have the weight matrix, you have this the particular input that is going in, and you have these bias terms that are getting added. So this is like just a dot product of these two, and you get a certain output. That again now, okay, correct. So this is what you kind of do like the neural network approach way. And this one where we were talking about this bias being this +1, this kind of is how you kind of represent that. Does this kind of make sense? This is just, yeah, I think pretty straightforward, the matrix notation and applying an activation function here. Activation function, yeah, right. So this activation function is what we've been kind of saying is the most important thing. And the reason why it's the most important thing is, imagine if you have two linear layers and a bunch of linear layers. Basically, if you have a set of linear layers, imagine your first one is multiplying everything by 2, the next one is multiplying everything by 3, and the third layer is dividing everything by 2. Though you're doing them as separate layers, this in essence can be just combined together as 2 into 3 divided by 2. So basically linear operations can be just combined together to just give you one linear operation. And that really doesn't help there is no, you're trying to build these curves, right, around so that you can kind of segregate these different inputs. To do that, to bring in this nonlinearity term is where you use these activations. And these activations are of a bunch of them are there. You have sigmoids, you have ReLUs, you have leaky ReLUs, etc., etc. And let's take you have for NLP kind of tan H is again a kind of common one that you use. So how is this nonlinearity kind of getting incorporated is you multiply WX plus B, you get a certain output. Now let's use, for example, ReLU. ReLU is just doing max of 0, whatever input you're passing it. So in other words, it's truncating all the negative values. So after you pass it through this ReLU function, you're going to get back positive. In other words, to kind of think about this is like, if you do a forward pass, let's say on just linear layers, that is multiplied by 2, multiplied by 3, divide by 2, you can kind of get back to your input in the reverse fashion. But whereas if you do this nonlinearity term, you kind of are losing information over there, very loosely speaking over there. You are losing some information, but which kind of helps you in building this nonlinear curves that help you segregate regions. So yep, nonlinearity is what and why. Like I said, that W1, W2, they're linear, so you combine them up, you can represent them as just one unit. Yeah, you haven't achieved anything. So for curve fitting and function approximation, you need to add in these. Actually, let's look at this. A lot of people must have already looked at it. It's pretty cool. Am I at the right one? This kind of looks at if you change these values. So yeah, this is what you're trying to do, right? You have a particular a curve that set of data, and you're trying to somehow fit something to it, either in terms of if it's classification, you're trying to build a boundary to separate both of them, or if it's like regression, you're trying to predict the value along that curve. Now, this again kind of deals with something called like the universal approximation theorem, where stacking these bunch of neurons like this with these linear layers with interspersed nonlinear layers is what kind of creates this. You can literally build any shape, and that's where kind of the name comes, like universal approximation theorem. You can approximate, in theory, given the time, given the amount of data, and the model is big enough, you should be able to approximate any curve, whatever you're trying to fit. So that's a cool site to kind of look at and read through that chapter. These are the examples of some of the activation functions. Yeah, this is kind of something we covered already, interaction terms. And if you're trying to look at what are my features, it's kind of really hard to look at that in terms of when a neural network kind of spits something back, if you're trying to make sense of the feature. But if you draw back to the word and vec, you remember the site, I think Alzheimer or one of those recommended blogs. The king, the queen, the boy, the girl, all those were represented by these colored vectors. But the thing was that when you looked at these colored vectors, you really didn't know what each color, or rather, if you looked down the column, you didn't know what that column really represented. So that's kind of a hard thing with this approach. Cool. Before we jump into named entity recognition, any questions over here? There's a bunch of slides that we have which kind of cover forward propagation and backward propagation. So if any burning questions are there before that, I can probably allude that we look at it in the future or anything else.
Yeah, Prashant, so I had a few questions. In the lecture, the professor was mentioning something about like window classification and using basically the model would be using 5 vectors.
Right, that is the named entity recognition.
I was kind of confused in that. I mean, can you please elucidate on that? I mean, how would the training model 5?
We haven't covered that yet. That's the next part.
Okay.
Yeah.
Perfect. Okay. Yeah. Okay.
So yeah, let's continue then. Okay. So named entity recognition. Yeah, there are a lot of holes in this that I don't understand. So please jump in. So basically, the objective of this is given corpus, you kind of want to say what entity does this belong to, and these are kind of the different entities that are possible: names of people, locations, organizations, pop songs, date, time, money, and kind of a use case. Why do we need this? Is basically like if you look through a news corpus and you're saying which companies were mentioned in the news article, so you want to know like where are the companies. So that kind of spits back. That's one of the use cases. Then if you're like this is another use case where specified products are mentioned in complaints or reviews that you're trying to quickly look up that. And I think this is even like at some point of time, Google used it, I guess, for like throwing up like similar clustered news items together. I may be wrong on that. So looking at this example, like say the European Commission, the European Commission is being tagged as, it's an organization, said on Thursday it disagreed with German, which is, they're tagging this as miscellaneous over here. France is a location, Britain is a location. So you kind of get an idea of what that is. Now, you want to predict these entities. Basically, it's again like a classification problem. You want to see these words into which class they kind of fall, whether it's an organization, whether it's a person, any of those. So this is the way they kind of encode these word sequences, right? So, foreign is an org, ministry is an org, spokesperson is none of them. This is a person, again, nothing org. Now, the problem with trying to encode something like this is, imagine there was another name here, Shenguang, something else. And then the problem is that those are two different persons, but if you're trying to look at them as this person, then the model kind of misrepresents that as all the three are like one name. So to kind of to take care of that, what they use is something called as bioencoding, or online I was saying it's also called as IBO. Basically, B is kind of the begin, I is inside, and O is outside. So it's something like if you were to have 3 words here, like I said, foreign, ministry, let's say there is, let's think of a better example.
Foreign service ministry.
Sorry?
I was just saying like foreign service ministry.
Yeah, exactly. Yeah, exactly. So yeah, if you have foreign service ministry, you would have BII. So in other words, to think of it as B is like beginning, I is like whether it's still part of this beginning, and O is like, that is where it kind of truncates. It's like, this is the end of it. So BIs, a starting B with followed any number of I's before you hit a O is basically one grouped entity. So that's what BIO encoding is. Yeah, you can check this link out. This is my attempt to kind of explain what this named entity recognition thing is. Let's say you're given this word Armstrong. Now, you don't know if it's Neil Armstrong, Louis Armstrong, if it's a place. I believe there's a place called Armstrong. It's a unit of length. So which one is it? Now, if I give you this picture, you kind of have context now. Now you know that I'm talking of which Armstrong, I'm talking of Neil Armstrong, most likely, that's the context. So that's what they talk about is, if you were to look at the way he talks about it is, let's pull up those slides actually. Right. Okay. So what you're trying to do right now is you take this specific situation where you're trying to do like, what is that called? Location, I think. Yeah, in Paris. So this is the one which has a location entity in the middle of the sentence, and this is what you're trying to predict. So the idea is you want to classify this word based on whatever the context window is. So we've already kind of familiarized ourselves with context windows in terms of word2vec. You're looking at your neighboring words and you're kind of making a decision. The problem with the strategy that they first try is that, how about we take these 5 words, take their representative vectors, average them out, and then make a prediction based on that to help classify whether Paris is the location in the center, Paris is the location entity in the center of this sentence or no. And okay, so the problem with that is you kind of are losing positional information, right? Now, this word museums followed by this preposition in seems super important to say that the next word that is going to follow is going to be a location over there. So that's what you take this X, they're representing this as each word is represented as a D-dimensional vector. And since you're using 5 words in this scenario, that's why X basically is 5D. So what they do is they take this X, they take the dimensions, the vector representation for museums, concatenate that with in Paris, concatenate that with, again, all these representations. And now you basically have this. So this is 5, and you have each of them is a 4D vector. I think that's what he makes the assumption somewhere. So that's how you get this 20 over here. So each word is represented by a 4-dimensional. So
Prasad, can you talk about how the vector is calculated? I mean, I understand that you get a bag of words. You're getting an index essentially for every word in the corpus, and then I understand that whatever king. I'm so tired of this example. King minus woman equals queen. And I get that they are in that vector space, but how was that calculated? Is it because I have the general idea it's calculating what words are around it, but do you know how those vectors actually get calculated?
Right. So there are kind of 2 approaches to that, which I think we'll be seeing when we kind of go into backpropagation. And the word2vec approach, if I'm not wrong, is you start off with randomly initialized values for this vector. So let's say you have made the decision that each word is going to be represented by a 200-dimensional vector. So now, let's say you have 100 words. So you have a matrix which is on the row is 100, column is 200 because that's the dimension you chose. Randomly initialize these, right? Now, any scenario of kind of like a supervised model that you're trying to do is you'll take this, multiply it, probably try to get an error. This is not exactly what happens in word2vec. I'm trying to think what exactly. Does someone want to jump in and remind me what exactly happens in word2vec? You take the representation, let's see. I forgot what the objective of the objective function there is.
Well, I could also try to look that up and report on it next week.
Yes, I'm just suddenly blanking, sorry. Yes, someone was saying something.
I guess in, I guess in word2vec what happens is you have words, right? And there are embeddings for each of the words in the corpus, depending on as Prashant was mentioning, right? Initially, they will be providing some weights, and the loss function, the theta that is calculated, they'll use a log loss after the model predicts, depending on the embeddings, right? And that's how, if you remember in the previous lecture, there were two matrices. One was the context and one was embeddings. Each of the word would have two separate vectors associated with it. And each of, sorry?
Yeah, right. Yeah, now, yeah, it came back to me. Yeah, makes sense. Yeah, go ahead.
That after the model predicts something, the embeddings, that's the input, gets updated, and finally we remove the context, the entire matrix, and we just use the embeddings to train the model. And that's how I remember things as. So I think that's how we get the final input vector where each of the word is represented using embeddings.
Yeah, David, I think that doesn't make sense. Actually, next week, I think the next assignment kind of covers implementing this. So I'm pretty sure we'll have a much better understanding of this. So we can kind of jump back onto that for sure.
Great, thank you.
Sure. Okay. So this is what kind of the end scenario was, where you have Paris in the middle of the sentence. You want to rate, this is what you want to give a high score. And now if you look at this sentence, not all museums in Paris, this Paris is not in the center. Looking at with respect to the context word, so you want to give this a low score. And this is again kind of treating it in this neural network approach that we've been talking of. He's concatenated this whole vectors for all these words. Then you have this intermediate layer, which is the one which is kind of with this activation. So that's going to incorporate the nonlinearity. So it's going to help the model learn and do this curve fitting much better. And at the end of the day, you multiply this with this U transpose, which kind of gives you a real number, whether it's a high score or a low score. I do not have a very good intuitive explanation for this one, unfortunately. I was just trying to draw out the matrix sizes. So you have X, which we decided, right, we were going to concatenate this. So that becomes a 20 by 1, given that the dimension for each word is 4. You multiply this into this weight matrix, add in this bias, and you have this, this is just what the sizes are. So here is where it is. You take this W, multiply it into this X, which kind of gives you an 8x1. You add in this bias 8x1. Important thing is, this is maybe obvious to some, when you multiply this weight, these layer operations that you're trying to do, you kind of change dimensions there. Important thing is that whenever you apply an activation, you never change the dimension as such. The dimension is always preserved. All you're doing is an element-wise operation. You're trying to either, like if you're using a ReLU, you're trying to do like max of 0, input. You're otherwise applying like a tanh function for each element individually. And so you finally get this, and at the end of you have this U transpose. Not extremely sure whether this is, I think this is something we again are trained. This is the U, right? So you train that. So these weights are also kind of updated. And then finally, when you multiply it into this 8x1 that you get, you are looking for a score, and this score you want it to be high when in the situation Paris is in the center, whereas a low score when Paris is not in the center. That was a lot of hand-wavy explanation, I kind of guess. I can share a video. I think it is from CS224, but I think it's the 2012 version where the professor kind of has a little more deep dive into this rather than this one where he kind of skims through. I tried figuring out what this loss function is that they use in this. I did not succeed. So if someone wants to add that, does someone want to do that? Or do you guys want to cover SGD, or this is kind of an important topic. So if you guys are saturated, you probably should start with SGD next time. This is kind of, I think, the most important thing that we need to kind of focus on. So what does everyone think?
I think Yeah, I mean, sorry. In regards to the last slide that you had mentioned regarding classification, even I'm not too clear. I mean, there were a lot of loopholes that I was trying to.
Right.
I mean, I have so many questions with the videos. I mean, I couldn't get answers to them. How the U metrics get calculated, how the what's the
U is basically
motivation?
this. How
is it getting?
Sorry, how is it getting calculated?
Yeah.
Okay. So U is so U is very similar
please.
to how you would train W or how you would train B. That's what my understanding is. So you basically want whatever this W is. So imagine, look at it like this. Here, if you were looking at this expression, right? Z is equal to WX plus B. What is it that you're seeing here? This is only X, right? The W and B is kind of hidden, which actually is sitting over here, which is you do X into this W and you add that B, which gives you this Z. Does that make sense to this layer?
Okay.
Right. So let's move to the next one now. So this is again the output, which is the A. And how do you calculate that A? It's basically you take the previous output, which is the Z, and you pass it through whatever activation function you want to pass it through. So you pass, so this is going to do that element-wise operation, you get this. Cool. Now you have the answer till this solution. Now the output from this goes into here. This U of T is similar to how this W and B were kind of hidden over here. That's also hidden right here, this U. You multiply this A into that U, which spits out, basically that's a dot product, right? U transpose into A. So that's like a row being multiplied to a vector. So the U has parameters, and these terms I've been throwing around parameters, activations, weights, biases. The next slides actually really kind of focus on what each of these are. And so this U gets calculated. UWB, these are all trainable parameters that you keep updating as you keep going.
Okay, so basically, if my understanding is correct, so basically, U initially would be randomly, generated or something. So U, W, and B would all be hyperparameters which would be trained for the efficiency, right?
So again, I think we should talk about what parameters are and what hyperparameters are. So parameters are something like this weight and biases. That is something that you will randomly initialize at some point of time, but the model will kind of figure out what they are. So that's what parameters are. And in kind of alluding to something that will come forward is parameters always refer to weights and biases. And parameters are something that you will always update. Activations are something that you always calculate. This is there in the future, so I'm just kind of covering that right now. And U transpose in this scenario is something, from my understanding, is something that will be calculated. W and B is also something that you're going to calculate over here, because you're trying to train this model and update these parameters W, B, and U. The only thing that you're kind of already given is because of the word vectors that you previously did from word to vec, you probably know how museums are encoded, I guess. You know how in is encoded. So you have some dimensions for that. I mean, you have some representation for that. So that is what I think is like the super cool part of, if you want to quickly look at that, this is what it is. You have, let us say, this is again going back to fast AI. This kind of talks of with respect to images. So we'll talk about with respect to images and then kind of draw a comparison with NLP. So let's say you have this, this is your 5x5 matrix, which is basically a W. Okay, so you have a certain image and you multiply that WX, right? So the X is the image and this is the W. So you have, this is initially like randomly initialized numbers. You multiply W into X, you get a certain thing. You can add in a bias, not added bias over here. So you add in the bias also if you want to. So you basically get this, you find this part, Z is what you have found right now, which is WX plus B. Now you move forward and you apply the activation function, which is ReLU, which I said was nothing but max of 0, X. Now, as I said, this is something that you're calculating and this is something that you're updating. Next, you move on And you have, so yeah, like I said, activations, when you apply an activation, you really don't change the shape. The shape remains the same. Once you get that output, after applying the activation, you multiply it into another weight matrix. This time it's 8 by 5. Again, you get an output. Again, you apply this nonlinearity to introduce your curve fitting thing, follow it by a weight matrix. Now you get an output, right? Now this output is what is kind of interesting. You apply a softmax, you do something, you kind of find out, let us say this, you're trying to distinguish between cat and dog. So this won't be like, oh, let's do digits, right? So you're trying to handwritten digits between 0 to 9. So one of these numbers is what you want ideally to pop out in this vector, which will basically indicate whether it's a 1, 2, 3, or whatever, up to 10, up to 9 rather. So let's say you get a certain high value here. This is what you predicted. This is what you have from your training set, what the actual number was. You subtract these two, that's what gives you the loss.
Error. So, right.
What we did right now is a whole forward pass. Basically, this doesn't help us so much with the deep learning part of it. The part that helps is, given this loss, you want to find the gradient of this loss and change these weights. These weights are what you want to change, so that next time around when you go about predicting this, it gives you a higher chance of getting that number right.
Perfect.
So that's
what exactly.
You keep going round and round and you keep updating stuff. So
one question before you move away from that. Sorry, before you move away from that, that image from FastAI, isn't there a mistake in there if you go back to it, which is, unless I'm misreading it. So there's the first weight matrix, the yellow, then the blue, then the output of 5, right, the purple. Then it's got that has 5 rows. So in order for the matrix multiplication to work, you would need 5 columns, not 8 columns. So isn't that backwards, that next one?
Right. So basically, you can kind of represent that as like taking it with a U transpose. So that's kind of, I agree. Like ideally, if it were to be written, yes, you would have to get, let us say 5 and this 5, yes. So then otherwise you can represent this, let's say like a row. That's what you're saying, right?
Okay.
Right. Yeah.
Yeah, exactly.
That's a good spot, yes, I agree.
Yeah. Okay.
I think
just checking.
I think Jeremy has evolved this notation that's a little bit more convenient than the standard notation that, the standard way we think of matrix multiplications, which Prashant has shown in his drawings and so on, which is very nice. But Jeremy thinks of it in terms of the way it works in a network. And in the network, it works sort of, you have the activation that gets multiplied by the weight matrix rather than the other way around. You go from start to finish. So the column 5 vector gets multiplied by the next layer. And so when he writes the purple 5 times the yellow, what he really means is the transpose. In other words, if you take W times X, and then you take the transpose of that, you get X transpose times W transpose. And that's the sense in which he means the X comes first and then the W transpose comes next. And so so really that should be a row vector. The purple vector with 5 should be a row vector multiplied by the transpose of the weight, and then that would give you another row vector. That's what
Yep, that is pretty confusing.
It is confusing, but if he would explain it better, it's kind of a nice way to think of things, because in the context of neural networks, you start with the input and then it gets multiplied by then it gets multiplied by the next layer, which then I don't know. It seems like it works from the first to the inputs to the end. It works better if you think this way, where the vector comes first and then the matrix comes after it. And then you can go from start to finish just by a repeated series of multiplications. But I agree that it's confusing and it's not explained as well as it could have been.
Right. That was a big issue, because linear notation, linear regression, if you were to look at a line, you always represent it as y is equal to mx plus b. And then suddenly you start looking at y is equal to xm plus b, and then it looks confusing. I agree
but
with
you
that.
could say in this, if you say y transpose equals x transpose m, that works. And I think that's what he's doing. Although to be more understandable, he should use row vectors instead of column vectors there, because that's what the transpose is. Anyway, that.
Yep. Or we should just probably, I think ideally just add a transpose up here, and that should solve the problem. I think then it keeps everything looks right and it follows the notation right.
Yeah.
Just a tree there, yeah. So like the next part is SGD. I'm at already 11:40. Do you guys want to continue, or do you think we should take over from next time? Because I tried. So people over here my survey said that there are a bunch of them already seen the Fast AI videos. So you already have seen the Fast AI implementation of SGD with Jeremy uses with linear regression. I kind of tried doing something similar without using PyTorch. So that notebook is also attached in the thread. So we kind of have to go through that also. Do you guys want to go through that now, or?
I would say maybe we should break off. At least I need to head out.
Okay, sounds good then. And I think let's convene next time so that everyone kind of goes through SGD.